Hello students, welcome to my lecture series on reinforced concrete structures. In this class, I am going to discuss about analysis of a doubly reinforced beam, that is a continuation of our previous class. Right. The outcomes of today's lecture are, on completion of this class, so you will be able to calculate numerically what is the total compressive stress or compressive force and what is the total tensile force which is acting on the member is. Then after knowing that compressive forces and tensile forces, you have to calculate what is the actual depth of neutral axis and what is the limiting depth of neutral axis. So if I equate that compressive forces and tensile force, we will get what is the actual depth of neutral axis, and limiting depth of neutral axis means the axis which is obtained when steel and concrete in a member attain its maximum permissible strains at the same time. The obtained from that condition is called a limiting depth of neutral axis. Then by knowing the total compressive forces, total tensile forces and actual depth of neutral axis, limiting depth of neutral axis, by using those parameters we can calculate what is the moment of resistance in this section. So in this lecture completely deals with the numerical problems for calculating moment of resistance for given dimension of a beam, grade of concrete, grade of steel and a number of bars provided in compression as well as tension zone. Based on that, we have to calculate total compressive forces, tensile forces, and then we have to calculate depth of neutral axis and limiting depth of neutral axis. After comparing depth of neutral axis and limiting depth of neutral axis, we may get what type of section it is, whether it is a reinforced balanced section or under reinforced section or over reinforced section. Based on that condition, we have to go for calculation of moment of resistance. Right. Let us recall what are the things we have discussed in last class. In the last class, we have discussed about what is the definition of a doubly reinforced beam and when we should provide this doubly reinforced beam, and for in which situation we have to provide this doubly reinforcement beam, doubly reinforcement, and what are the steps for finding moment of resistance. So let me brief one by one here. So what is the definition of doubly reinforced beam means? It means the reinforcement provided in both the zones of a beam. For a beam we have a tension zone and a compression zone. If you provide the reinforcement in tension zone and as well as in compression zone, then I can say this beam is a doubly reinforced beam. So when we have to provide this will be provided when your applied bending moment is more than limiting bending moment of a beam section. Then only we have to provide a compression reinforcement in the beam. So what are the situations for providing doubly reinforcement is? So here, as we know that your mu is greater than mu limit, the way of increasing your mu limit is based on we have two choices, and the first one is we have to increase the depth, but sometimes the depth of the beam we cannot increase because of some architectural appearance or architectural constraints, I can say, and over a headroom, if you want to construct a headroom over that, there is no possibility of increasing depth of a beam. So that option is not 100%, we cannot adopt. So the second option is increasing the limiting moment of resistance of a beam by providing reinforcement. If you provide the reinforcement, additional reinforcement in tension zone, then it will become a over reinforced section. So as per our recommendations given by IS 456-2000, over reinforced sections are not designed and they are not advisable also because they are unsafe and uneconomical. As you know why it is uneconomical and why it is unsafe is. So only option we have is to provide the reinforcement in compression zone, then we can increase our limiting moment of resistance so that we can make our section stable, or we can resist the bending moment which are coming due to the externally applied force. So those are the, and we have situation like when we have the force may act from the both side. If you apply the force from this side, we will get the bending moment like this, and sometimes we may get the force from bottom also, then we get the bending moment will be like this. It will bend from bottom like this and will bend from top it like this. To overcome this problem, we have to provide a reinforcement in compression as well as in tension zone. And generally, doubly reinforced sections are adapted in seismic zones where earthquakes are frequently occurs. So in this situation, the earthquake forces may damage your building or damage may structure. So because of ductility property of this steel, this can withstand, or this can it will give the warning before collapse of a structure or a member. So this is the reason why, or this is a situation where we are providing doubly reinforced sections. So let me brief that what are the steps for finding out the moment of resistance. So first of all, we have to calculate what is the FSC is. What is FSC? It is a stress in compressive steel. The stress induced in the compressive steel that can be calculated based on the D dash by D ratio. What is the D dash? D dash is a effective cover provided in the compressive zone. And you know the D is effective depth, and from that ratio we will calculate what is the FSC is. According to the table number F of special publication 16. Generally it is called as a SP16. In the SP16 there is a tables are there for particular ratio of D by D. There we have to, for particular grade of steel, we have to calculate what is the FSC is. Those things we are given in table in our previous classes also. So let's see in this class also. That is the first step. Second step, we have to calculate what is a depth of actual neutral axis, or the actual depth of neutral axis is. That can be calculated by using equating the total compressive forces equal to total tensile force. From that we can calculate what is the XU is. After obtaining the XU, we have to calculate what is limiting depth of neutral axis, or I can say a maximum depth of neutral axis. That can be calculated based on the grade of steel, and there are some ready-made formulas given in your IS 456 2000. Say for example, for Fe 415, the XU max can be calculated 0.48 into D, small d. Small d is the effective depth. Like that we can calculate the limiting depth of neutral axis for various grade of steel. Then in third step, we have to, in fourth step we have to compare what XU and XU max. And if your XU is less than XU max, then I can call it as a under reinforced section. If XU is greater than XU max, it is a over reinforced section. If XU equal to XU max, then I can say it is a balanced section. So generally we will design under reinforced sections for economy and safety point of view. So sometimes you may get, that is XU is greater than XU max. That means your actual depth of neutral axis may get the maximum depth of neutral axis or limiting depth of neutral axis. Then we have to substitute the maximum depth of neutral axis for in place of actual depth of neutral axis in the moment of resistance formula that is provided in your code book, or I will explain here also. So with these steps, now we will solve some numerical for calculating moment of resistance of a doubly reinforced beams. So let's see the first numerical. That determine the factored bending moment of resistance of a beam of size 230 by 460 mm effective depth. So here remember that is a width, and this directly has given what is the effective depth is. That is 460 mm is effective depth, and the beam is reinforced with two 16 mm diameter bars on compression side. The compression reinforcement is provided is 2 bars of 16 mm dia in compression zone, and in tension zone 4 bars of 20 mm diameter are on the tension side. Okay, the compression bar are placed at a distance of 40 mm from the top. So this I can call it as effective depth. It is a effective cover in the compression zone, that is a D dash. And by using M20 grade and Fe 415 steel, we have to calculate the moment, the factored moment of resistance of this doubly reinforced beam. So how we are calling it as a doubly reinforced beam without mentioning the word called doubly reinforced? Here you can know from the reinforcement provided in the beam. Here the reinforcement provided in compression side as well as in tension side. So when the reinforcement provided in both the zones of a beam, then I can call it as a doubly reinforced beam. If it is provided in only one tension zone, then it is a singly reinforced beam. So in the problem, we have provided the reinforcement in both compression zone as well as in tension zone. So it is a doubly reinforced beam. For this doubly reinforced beam, we have to calculate what is the factored moment of resistance is. So according to this problem, now we have to write what is the given data is. So in the problem, it is mentioned that the width of the beam is 230 mm, the effective depth of the beam is 460 mm, and grade of concrete M20, the corresponding characteristic compressive strength of a concrete is FCK is equal to 20 Newton for mm square, and grade of steel is given is Fe 415. The characteristic strength of a steel, that is Fy equal to 415 Newton for mm square. Right, and in addition to this, he has given the number of bars and diameter of bars are provided in compression zone as well as in tension zone. According to that, we have to calculate what is the area of compression reinforcement and what is the area of tensile reinforcement. And also mentioned in the problem that is effective cover in compression zone is T dash equal to 40 mm. Right. Let me calculate first what is the area of compression reinforcement ASC is. In the problem, it is given that 2 bars of 16 mm diameter. So for that corresponding area we have to calculate. So that number of bars are 2, and we know the bar cross section is circular cross section. For area of cross section for circular section is pi by 4 d square. In place of d, we have the diameter given for the bar is 16 mm. If you calculate this, we will get 402 mm square. So the area of compression reinforcement ASC is 402 mm square. Similarly, calculate area of tension reinforcement, that is AST. So in the problem is given that 4 bars of 20 mm diameter on tension side. So for the particular 4 number of bars, we have to calculate what is the total area provided in tension zone. So 4 bars, 4 into pi by 4 into d square. Here d is 20 mm. So 20 d square means 20 square here. If we calculate this value, we'll get that is 1256 mm square. So now we got what is the ASC and what is AST. Then we have to calculate what is the ratio of d dash by d for knowing what is the value of Fsc. So d dash by d equal to d dash is given 40 mm and effective depth is given 460. So from that we can get the ratio is 0.0869, which is less than 0.2. Generally in table number F of SP16 has given the values up to 0.2 only. So that's why the value, that's why we have to check for that. Otherwise we go for further calculation. If we get this value greater than 0.2, then we go for other methods like by calculating strain from the graph. We have to calculate what is the corresponding stress is, right? So now by calculation we got our d dash by d value is less than, that is 0.2, that equal to 0.0869, right? So let us see the steps for procedure to find out moment of resistance. In that, the first step is by knowing d by d ratio and grade of steel, we have to determine the Fsc. So in this problem, the d dash by d ratio value is 0.0869 and the grade of steel given is Fe 415. From table number F of SP16, the SP means special publication 16 related to RCC design. So here the table are given. In this table, vertically they are given grade of steel and horizontally they are given what is the d dash by d ratio is. But the d dash by d ratio, if you see here, that is 0.05, 0.1, 0.15 and 0.2. But our value obtained is not exactly fit to this table. They are also given a note that for intermediate values of d dash by d, the next higher value may be used for finding Fsc from the above table. So according to this problem, we got the d dash by d is 0.0869. It is neither 0.05 nor 0.1. It is in between these values. But in the note, it is in the SP60 it is said that you have to take next higher value for calculating Fsc. What is the next higher value of this? 0.0869, that is 0.1. Right. Now what is the grade of steel given? That is Fe 415. So Fe 415 steel, and for corresponding 0.1, what is the Fsc, that is stress in compressor steel is 353 from this table. So finally I can take the Fsc value corresponding to the d dash by d, that equal to 0.1. From that I got, that is Fsc is equal to 353 Newton per mm square. So this is all about first step. After calculating first step, that is Fsc, then we go for calculating the second step, that is actual depth of neutral axis. So you know how to calculate actual depth of neutral axis. There is a formula we have. This formula is obtained by equating total compressive forces equal to total tensile force. If we rearrange the term, we will get Xu equal to 0.87 Fy AST minus Fsc into ASC whole by 0.36 Fck into B. Now substitute all the parameter known to you in this equation, will get what is the Xu is. So let's substitute 0.87, Fy is 415, AST is area of tension reinforcement, that is 1256, minus Fsc is, just now we have calculated from our previous step, that is 353, and area of compression still given is 402, whole by, that is 0.36, Fck is grade of concrete. The grade of concrete is given 20, M20 grade, so 20, and width of the beam given 230. If after calculation all those things, will get your actual depth of neutral axis, that is Xu is equal to 188.15 mm. So after knowing this, you have to calculate what is the limiting depth of neutral axis is. So as I told you, the limiting depth of neutral axis is depend upon a grade of steel. There are a ready-made formula for calculating limiting depth of neutral axis as per IS 456-2000. The given grade of steel is Fe415, corresponding limiting depth of neutral axis is 0.48 D. So now substitute D value and calculate what is the limiting depth of neutral axis is. So Xu max equal to 0.48 D, and 0.48 D multiplied by effective depth, that is effective depth value given in the problem is 460. So corresponding corresponding the value of Xu max is 220.8 mm. After calculating, we will obtain the Xu max value is 220.8 mm. So after calculating actual depth of neutral axis and limiting depth of neutral axis, in fourth step you have to compare what is the Xu and Xu max. What is the relation exists between these two? Now from this, Xu is 188.15 and Xu max is 220.8. If you compare this, your Xu is less than Xu max. So according to our conditions, so this section is decided as under reinforced section. For the under reinforced section, the moment of resistance can be calculated with respect to this. So in the double reinforced section, only option we have for calculating moment of resistance is with respect to compression only. Because with respect to tension, we have seen the problem if you use that problem. If here we are dividing the total section two sections, that is we have to calculate what is the AST1 and AST2. We cannot divide number of bars corresponding to AST1 and what is the number of bar corresponding to AST2. So that is very impossible to calculate. That's why we are depending upon the moment of resistance calculation with respect to the compression zone only. Right. Now calculate the ultimate moment of resistance with respect to this formula, that is mu equal to 0.36 Fck B into Xu whole multiplied by D minus 0.42 Xu plus Fsc minus Fcc into Asc or into D minus D dash. This formula can be modified as like this, because compared to this Fsc value, FCC value is very less, so we can neglect that term. Finally, after neglecting that, so we will get the ultimate moment of resistance formula 0.36 Fck B into Xu into D minus 0.42 Xu plus Fsc into Asc whole into D minus D dash. If you substitute all those values in this formula, that is Fck, B, Xu and all, we will get what is the ultimate moment of resistance is. So it is 0.36, Fck is 20, B is 230 and Xu actual depth of neutral axis is 188.5 and effective depth is 460 minus 0.42 Xu is already actual depth of neutral axis we have calculated, that is 188.5 plus, and this is a compressive stress in compression reinforcement, that is 353, that we have calculated from the table number F of SP16, and ASC is area of tension compression reinforcement, that is 402, and D minus 460 minus 40, you will get, that is mu equal to 178303962 Newton into mm. If you want to convert that into kilonewton into meter, divided it by 10 power 6, we will get mu equal to 178.3 kilonewton into meter. So this is the moment of resistance corresponding to the data given in this problem. So next we will solve one more numerical here, that is Determine the factored moment of resistance of a beam, that is 300 by 450 effective depth. Again he is given effective depth. The beam is reinforced with 220 mm diameter bars on compression side and 425 mm diameter bars on tension side. The compression bars are placed at a distance of 50 mm from the top. That means it is the effective cover in compression. For this, use M20 grade concrete and Fe415 steel. Right. Now tell me, dear students, what type of beam it is? It is a doubly reinforced beam again. How we are saying it is doubly reinforced beam? There is no word mentioned called doubly reinforced here. So we can call it as a doubly reinforced beam based on the placing of reinforcement. So in the problem it is given that 220 mm diameter bars in compression zone and 425 mm diameter bars are provided in tension zone. So here finally the reinforcement is provided in both compression and tension zone of a beam. So then I can say it is a doubly reinforced beam. Right. So based on this problem we have to write what is the given data is. The width of the beam given is 300 mm. Effective depth is 450 mm. And for M20 grade, the characteristic compressive strength of a concrete is 20 Newton for mm square. And for Fe415 steel, the characteristic strength of a steel is 415 Newton for mm square. As in the problem, it is mentioned that the number of bars and diameter of bar provided in compression zone as well as in tension zone. According to that, we have to calculate what is the area of compression reinforcement and area of tension reinforcement. So in addition to this, he has given the effective depth of a compression reinforcement, that is d dash is equal to 50 mm. Right. Now calculate the area of compression reinforcement. ASC is equal, the number of bars given 2 and diameter of bar is 20. So pi by 4 into d square. In place of d you have to substitute what is the diameter of bar is. The diameter of bar given in the problem is 20 mm. If we calculate, then we will get ASC is 628 mm square. Then similarly calculate what is the area of tension reinforcement, that is AST. In the problem it is given that 4 bars of 25 mm diameter of bars. Now 4 into pi by 4 into d square is the diameter of bar given, that is 25 mm square. Finally the area of tension reinforcement AST is 1964 mm square. Right. Then we have to calculate the ratio of d dash by d, that is effective cover provided in a compression zone to the effective depth of the beam. From that we can calculate what is the stress in steel under compression zone. So d dash by d equal to, d dash is 50, the effective depth of beam given is 450, then the ratio of that is 0.11, it is less than 0.2. Why I am comparing with this 0.2? In the table number F of SP16, the table is up to the ratio of 0.2 only. That's why I am comparing, whether it is less than 2 or greater than 2. So the value obtained for d dash by d is less than 2. So I can adapt the table number F for calculating FSC. So then first step, calculate what is FSC. FSC can be calculated from the ratio of d dash by d to the given grade of steel. In the problem, the d dash by d ratio is 0.11 and the grade of steel given is Fe415. So according to the table number F of SP16, so there is no exact value for d dash by d ratio 0.11. And in the note it is mentioned that for intermediate values of d dash by d, the next higher value may be used for finding FSC from the above table. So in the table it is given 0.1. What is the next your d dash by d value falls between 0.10 and 0.15. So according to this note, we have to take the next higher value. What is the next higher value? That is 0.15. So we have to calculate FSC corresponding to the d dash by d ratio of 0.15. So if the take FSC value corresponding to d dash by d equal to 0.15, that value is, say for Fe415 steel, the ratio is 0.15, that FSC value is 342 Newton for mm square. So this is how we calculate FSC by using the given condition. Next we have to calculate what is that actual depth of neutral axis. So you know the actual depth of neutral axis is calculated based on equilibrium condition, that is by equating total compressive force acting on the member to the total tensile force acting on the member. So if you equate that and rearrange the terms, we will obtain the formula called XU is equal 0.87 Fy into AST minus FSC into ASC whole by 0.36 FCK into B. Now substitute one by one here. 0.87, Fy is 415, AST is 1964, that is area of tension steel, minus FSC is already calculated from your previous step according to the D dash by D ratio and the given grade of steel, that is 342, and area of compression reinforcement is 628. This whole by this factor, that is 0.36, FCK is grade of concrete given 20 Newton for mm square and width of the beam is 300 mm. So if after calculating this value, we'll get the actual depth of neutral axis XU is equal to 228.85 mm. After calculating actual depth of neutral axis, then we have to calculate what is the limiting depth of neutral axis is. So limiting depth of neutral axis depends upon the grade of steel. For given grade of steel, there is a ready-made formula for calculating limiting depth of neutral axis according to the IS 456-2000. So the given grade of steel is Fe415. The corresponding XU max, that is limiting depth of neutral axis value, is 0.48 D. So right here XU max equal to 0.48 D, and then the D value is effective depth of the beam that is given in the problem, that is 450 mm. By calculating this value, that is 0.48 into 450, we will get XU max is 216 mm. Then now in next step, in step number 4, you have to compare our actual depth of neutral axis and limiting depth of neutral axis. So actual depth of neutral axis obtained is 228.55 mm and actual depth, maximum depth of neutral axis is 216 mm. The relation exists between these two is our actual depth of neutral axis XU is greater than limiting depth of neutral axis or the maximum depth of neutral axis XU max. According to the condition, we know if the XU is greater than XU max, this section is called it as a over reinforced section. Here XU is greater than XU max, so we can call it as a over reinforced section. So as per IS 456-2000 in limit state method, over reinforced sections are not desirable, so we have to design it as a balanced section. So to design balanced section, in place of XU, we have to substitute XU max for calculating moment of resistance. So the formula will be like this: in place of XU, we have substituted XU max. Then based on the value obtained for XU max, we have to calculate ultimate moment of resistance by using these formulas. That is mu equal to 0.36 FCK B into XU max. Usually it will be XU, but it is a over reinforced section. In place of XU, we have to substitute XU max. That means we are calculating moment of resistance with respect to the balanced section, right? So that is lever arm, the D minus 0.42 XU max, and we have one more factor, that is plus FSC minus FCC whole into ASC into D minus D dash. As this FCC value is very low compared to FSC, that's why we can neglect this value. So the modified formula will be like this for calculating ultimate moment of resistance: mu is equal to 0.36 FCK BU XU max into D minus 0.42 XU max plus FSC ASC into D minus D dash. Now substitute 0.36 FCK is 20 into B is 300, XU max is 216, and effective depth of the beam is 450 minus 0.40 into XU max is 216 plus FSC is 332. This was calculated according to this table number F of SP16, and ASC is 628 and D is effective depth 450 and effective cover and compression zone D dash is 50. After calculating this, we will get the value of ultimate moment of resistance, that is 253536076 Newton into mm. If we convert into kilonewton into meter, then divide this value by 10 power 6, we will get mu is equal to 253.53 kilonewton into meter. So this is how we calculate the moment of resistance when we get the over reinforced section. Dear students, just see the difference between under reinforced section and over reinforced section for calculating their ultimate moment of resistance. It is clear that when it is a under reinforced section, you have to use as it is whatever the XU value you got, the same XU value you have to substitute in the moment of resistance formula. If you are getting over reinforced section, so as per code, it is not permit to design or calculating moment of resistance the over reinforced section. So that section, the moment of resistance for that particular section, we have to calculate corresponding to the balanced section. So for balanced section, the depth of neutral axis must be equal to the maximum depth of neutral axis. So in place of XU, you have to substitute what is the XU max and finally calculate what is the moment of resistance corresponding to the over reinforced section, that is in terms of balanced section. Right. So we'll see the next variety of problem, that is determine the factored moment of resistance of a reinforced concrete beam of size 300 by 400 mm depth. See, in previous problem here he has mentioned that is effective depth, but he never mentioned anything here. He simply said depth means it definitely a overall depth, right? Now the beam is reinforced with 3 18 mm dia bars in compression side and 6 18 mm dia bars in the tension side, and effective cover is 35 mm on both sides. That is effective cover 35 mm in both sides. So use M20 concrete and Fe415 steel. Here you have to decide what type of reinforcing beam is, whether it is a singly reinforced beam or a doubly reinforced beam. So according to this problem, the reinforcement provided in compression zone as well as in tension zone, so I can call it as a doubly reinforced beam. In addition to that, he has mentioned what is the effective cover in both compression zone and tension zone. Both are same, that is 35 mm. So how to calculate a effective depth when overall depth is given? That is overall depth equal to that is effective depth equal to overall depth minus effective cover. Right, here the B is 300 mm and overall depth is 400 mm. Effective depth small d is equal to 400 minus effective cover, that is given 35, so that is 365 mm. And given grade of concrete is given M20, for that FCK is 20 Newton for mm square. Grade of steel is Fe415, for that Fi equal to 415 Newton for mm square. So in the problem it is given that the area of rain, the number of bars and diameter of bars in compression as well as in tension. So according to that we have to calculate what are the area in tension zone and what is the area of steel in compression zone. And effective cover given in compression zone, that is d dash equal to 35 mm. It is directly not mentioned that 35 that compression zone effective depth. He has given in the problem that the effective cover 35 mm on both sides. That means that is in compression side and tension side. So I can write d dash equal to 35 mm. So area of compression reinforcement ASC can be calculated, that is 3 into pi by 4 into d square. Here 3 is the number of bars and d is the diameter of bar provided. If you substitute the value of d in this equation, we'll get that is 3 into pi by 4 into 18 square, we'll get 736.4 mm square as area of compression reinforcement. Similarly, we have to calculate what is the area of tension reinforcement is. So area of tension reinforcement AST equal to number of bars multiplied by area of cross section of that particular bar, that is 6 bars are there, and area of cross section pi by 4 into d square, and the diameter of bar given in tension zone also 18 mm. So if we calculate all those things, we will get here the area of tension reinforcement provided in the tension zone equal to 1526.8 mm square. So after obtaining this ASC and AST, then we have to calculate what is the ratio of d dash by d. That means d dash is a effective cover in compression zone and small d is the effective depth of the beam. So effective cover in compression zone is 35, effective depth is 365, the value obtained is 0.096. That value have to compare with the maximum value of table number F of SP16. The maximum value of d dash by d dash is 0.2. So this value is well below the 0.2. So we can adopt the table for calculating FSC. So according to step number 1, step number 1 is corresponding to what? Ratio of effective cover in compression zone to the effective depth, that value, and the grade of steel. According to this problem, the D dash by D ratio is 0.096 and grade of steel given is Fe415. The FSC value can be calculated from table number F of SP16. The table is provided here for you. That see, the value is 0.096 D dash by D value, but direct value of that ratio will not find in this table. In the note, it is given that for intermediate value of D dash by D, the next higher value may be used for finding FSC from the above table. So this is 0.096. The next higher value of this is 0.1. So the FSC can be calculated corresponding to the D dash by D value of 0.1. For that, FSC is 356. Say the given grade of steel is Fe415 and assumed depth of assumed ratio is 0.1. So corresponding value will be 353 Newton for mm square for compression stress in compression steel. Then second step, we have to calculate what is the actual depth of neutral axis. This can be calculated by equating total compressive force acting on the beam to the total tensile force acting on the beam. After rearrange terms of those equation, will get XU. XU is equal to 0.87 Fy AST minus FSC into ASC whole by 0.36 FCK into B, and substitute the values what we have in given data in this equation. We will get what is the XU is. Say 0.87, Fy is 415 and AST obtained is 1526.8 minus FSC, that is compressive stress in compressive steel, is 353 and ASC is 763.4 whole by 0.36 FCK is 20 and B is given in the problem, that is 300 mm. After calculating this, we will get the actual depth of neutral axis. XU is equal to 130.3 mm. Then calculate what is the limiting depth of neutral axis, that is XU max, or I can say XU limit also. This value depends upon grade of steel what you are using in this problem. The grade of steel is Fe415. The corresponding XU max is 0.48 D. Just write that equation here. XU max equal to 0.48 D. From 0.48 D, D is effective. What is that? Effective depth. That is generally in this. I think it is in the problem. It is given 400. Please correct it. Just write it here. 0.48 it into 400. This value will be correct. That is 175.2 mm. So dear student, just make it note here. Instead of 365, please write here 400. Is this 400 or 365? Let me check. Sorry, it is 365 only, as 400 is the overall depth. So after that we have calculated what is the effective depth, that 365. So sorry, keep it as it is. That is 365 only. The 0.48 multiplied by 365 will get 175.2 mm. Then compare XU and XU max. So XU equal to 130.3 mm, XU max equal to 175.2 mm. And the relation exists is XU is less than XU max. So the type of beam section is under reinforced beam section. So under reinforced beam section, the moment of resistance can be calculated by using this formula. Next, calculate moment of resistance, that is ultimate moment of resistance, using this formula, that is ME equal to 0.36 FCK BXU into lever arm, that is Z minus 0.42 XU plus FSC minus FCC whole into ASC into D minus D dash. This equation can be modified further like this, because this FCC value is very less compared to FSC, so we can neglect that term. Finally, MU equal to 0.36 FCK B into XU into D minus 0.42 XU plus FSC into ASC whole multiplied by D minus D dash. If we substitute the value of FCK, XU and FSC and ASC, then we will get what is the ultimate moment of resistance. Let us substitute 0.36, FCK is 20, B is 300, XU is 130.3 and D is 365 minus 0.42 into XU is 130.3 and FSC is 353 that we have calculated from a table number F of SP16 according to the ratio of D dash by D and grade of steel. So ASC is area of compression steel, that is 763.4 into 365 minus the effective depth of effective cover in compression zone is D dash 35. After that, after calculating this value, we got ultimate moment of resistance is equal to 1763.63962 Newton into mm. if you want to get this value in terms of kilonewton into meter, just this value divided by 10 power 6 will get the ultimate moment of resistance corresponding to the values given and the dimensions and parameters given in this problem will be mu equal to 176.36 kilonewton into meter. Right. So let me summarize what we discussed today. We have seen the three variety of problems. First problem is when effective depth and area of tension reinforcement and area of compression reinforcement and grade of steel and concrete is given, then we have calculated what is that the FSC value, then XU value, XU max value. By comparing XU and XU max, we got that if it is an under reinforced section, we will go with as it is. There is a moment of resistance corresponding to the compression. Right, in second problem, we have obtained that it is a over reinforced section, that is XU is greater than XU max. For that, what we did for calculating moment of resistance is, in place of XU, we have substituted XU max. Why? As per our codal restrictions, we cannot design that over reinforced section. So, if we get the over reinforced section also, we have to restrict our section for calculating moment of resistance corresponding to the balanced section only. So in place of XU, there we have to substitute XU max in moment of resistance of a compression with respect to compression zone. There we substitute XU max, we will get what is the moment of resistance is. So these are the things we have discussed in today's class. So thank you for your patient listening. That's all for today's lecture.